In part 2 of the finale of our series on limits, we looked at various multiplication laws of limits, as well as the division law. If you haven't watched it, check it out at the end of the video. But for part 3 on our laws of limits, we're going to look into embedded limits and limits of powers. So let's take a moment and try to clarify what I mean here. So when I say embedded limits, what is it that I'm talking about? What does embedded mean? Well, to put it simply, it's just what happens when you take a function of a function. So what does that mean for limits? Well, if I take the limit of some function, but within that function is another function, then I can take the limit of the inner function and then use that limit in the outer function. In a second, we'll take a look at this rule in more detail, and it'll make a little bit more sense. Now, the other part of what we're looking at is the limits of powers rule. And I think it sounds pretty straightforward. It happens whenever you take a function and raise it to a power. In terms of limits, what that means is that I can take a limit of a function raised to a power, and that's the same thing as taking the limit and raising that to a power. Basically, the ideas that make these laws work are the same ideas that make our previous laws of functions work. With limits, order is relaxed. It's not important, but it is relaxed. And so hopefully this explanation of limit laws takes off the scariness of limits a little bit more. Let's take a look at some examples. So first, taking a look at embedded limits, we're finding the limit as x approaches pi of cosine sine x. Now, to be clear, we are not doing cosine times sine x. That is not true, but rather sine x is the argument for cosine, meaning that the sine is actually an embedded function of cosine. So according to our embedded limits law, instead of trying to take the limit of this entire function, we could take the limit of sine x first. And so as long as we don't get an undefined answer by plugging in x, we can just plug in x. What is sine of pi? Sine of pi is 0. I'm planning on making a series all about trigonometry functions, so stay tuned for that. But now we have to find the cosine, not of sine x, but of 0, of our limit of sine x. And the cosine of 0 is in fact positive 1. So the limit as x approaches pi of this function is 1. It was a very quick and simple problem, but let's take a look at a slightly trickier one. Here we have another example where we're trying to find the limit as x approaches -7 from the right of a pretty chunky. Well, this limit is a little bit harder to deal with. Why? Because very clearly we have one function right there, or two if you want to count each side, that's okay too. But then that would be the division law of limits, not the embedded limits. So what's the other function? Well, believe it or not, the other function is actually the square root itself. Although the square root doesn't really have any numbers alongside it, the square root function is the inverse function to squaring. So in that regard, the square root function is actually the second function if we think about it. And so we can use the embedded limits law yet again. Now this limit is much easier to solve than the one that's up here. Now if x is approaching -7 from the right, meaning that we're choosing numbers greater than -7, then what happens to this function? Well, we could work out what's up here, but what's more important is that -7 plus 7 equals 0. This is way more important. Why do I say that? Well, a denominator of 0, as we've seen before, approaches either positive or negative infinity. And so the only other thing we need to do is determine whether or not it is positive or negative. So since we're going from the right, let's use a number like -6. -6 plus 7 is positive 1, so the bottom is positive. And if we use -6 for the top, we get an answer of 28, which is also positive. And remember, the only thing that matters is that it gets more positive, because as we get farther away from -7, then the answers only get bigger and bigger and bigger. Oops, I guess I erased the square root at some point, my bad. So therefore, by doing this limit on the inside first, we are taking the square root of positive infinity. And what is the square root of positive infinity? Well, it's positive infinity. And so as x approaches -7 from the right, this entire function approaches positive infinity. So in my opinion, the limits of powers rule is actually a much more useful rule compared to the others. And here you could probably see why, because here we're raising x plus 2 to the 8th power. Now, I don't know about you, but I wouldn't want to multiply x plus 2 8 times. Remember, multiplying this out would give us some 8th degree polynomial, and trust me, we do not want that. Well, the limits of powers rule makes this so much easier. How come? Well, instead of multiplying this out 8 times, first we can find the limit of this function right here. Now, this limit is much easier for us to solve. So as x approaches negative 1.5 of this function, what do we get? Well, we can just plug in negative 1.5 for x and we get 0.5. Or if you wanted to express it as a fraction, 1/2. But either way will work perfectly fine. Now let's not forget though, 1/2 is the result of the limit of our function, but it is not the result of that function to the 8th power. So according to this law that we're working with, all we have to do is raise 1/2 to the 8th power, and then what do we get? Following our rules of exponents, we get 1 over 256. So the result of our limit up here isn't 1/2, remember we can't forget the power, it's 1 over 256. Let's take a look at one more example here. Here we're trying to find the limit as theta approaches 0 of this trigonometric function right here. Now there's a few things going on here. Of course, we're raising sine to the 4th power, and then we're multiplying that by cosecant. So we could find the limit of each. However, this may not be necessary. How do I know that? Well, we're multiplying sine to the 4th by cosecant. What is special about cosecant? Well, cosecant is the reciprocal sine function. Meaning if sine is just sine, obviously that makes sense, cosecant equals 1 over sine. Maybe if we redefined sine theta as a, then that would basically be the same thing as saying a to the 4th times 1 over a. Now looking at this is a lot easier to do. So naturally, like any reciprocal does, it cancels out with its original term. However, we're not eliminating all of the signs. No, remember, this is sine to the 4th, so we would end up with sine cubed theta. This looks much more doable than our last problem. So now we can find the limit as theta approaches 0 again. And using our power rule, we can find the limit of sine, and knowing that sine of 0 is 0, we can also raise 0 to the 3rd power, and we get an answer of 0. Now, even though we can't plug in 0 for cosecant theta, our limit still outputs a value of 0. Do you like eat donut? So what are the key takeaways that we should keep in mind going forward? Well, first off, before we do any of that, you need to give yourself a massive round of applause. Because if you stuck with me from the beginning of this series, you did it. You made it through. If you didn't, then you have to go all the way back to the first video, watch it through, and then you get the prize. But anyways, key takeaways. Today, we talked about the limits of powers law and the embedded limits law. And so we should remember that a common theme between not just these two, but also all other limit laws as well, is that limits aren't as scary as one might think. Limits, if you know the basic idea about them, are pretty lenient. But at the end of the day, we can rest knowing this above all else. Limits are about approaching, not equaling. Are there any STEM topics you want to discuss in the future? Let me know down in the comments below. I would be thrilled to hear from you. But until next time, keep working hard, don't give up, and always ask questions.